Okay, it's my second video on collisions in 2D. Here's the question, have a look, give it a go, pause the video, and then come back when you're ready to see the answers. Okay, so we've got another angled wall problem. Okay, we know the initial velocity. Okay, we know the final velocity. We don't know the coefficient of friction. Okay, that's the whole goal of this question, is to find the coefficient of friction. Okay, however, they're not dropping us straight in the deep end. Okay, they've given us a part A saying, show that the wall AB is parallel to 2, 3. Okay, now, initially, that looks like a very hard thing to do because we've got no information on the wall whatsoever. However, we need to use an important fact here, and it's quite a high level fact, and that's that the wall, okay, which I'm going to denote as the wall vector capital W, is always perpendicular to the impulse, i.e. the dot product of the wall and the impulse always gives you 0, okay, because if we look at the impulse here, okay, the impulse acting on the wall always acts perpendicular to the wall, okay, so all we actually need to do is find the impulse, and then we can use this fact here to work out the wall vector, okay, which is just a vector parallel to the wall, okay, which will hopefully give us 2, 3 or some multiple of 2, 3. So let's start off by actually just working out the impulse on the ball. So we know that the impulse is given by the mass times the change in velocity, okay, so m times the final velocity minus the initial velocity. Now, the important thing here is that the impulse equation isn't just used in one dimension. It can be used in 2, 3, 4, however many millions of dimensions that you can make up. Okay, so the impulse, okay, equation can be written like this with vectors instead of scalars. So let's do this, okay, but remembering the mass is always a scalar. Okay, that's not going to be a vector. So the impulse on the ball is given by the mass, so 0.5 kilos times a change in velocity. Well, the final velocity is 1/6. And the initial velocity is 7.2. So we get a half times 1 minus 7 is minus 6, and 6 minus 2 is positive 4. Okay, so we get minus 3, 2. So this is a vector parallel to the impulse. In fact, this is the impulse because we've used the impulse equation to determine it. So this is the impulse on the ball, minus 3, 2. And we can say that the impulse, okay, we have to state this to the examiner, the impulse dotted with the wall vector always gives 0 because they are parallel, okay, so because they're perpendicular, okay, excuse me, so because impulse and wall are always perpendicular, okay, so we know that we can plug our impulse equation into our W, so we get that the impulse, okay, dot W equals 0, so the impulse minus 3, 2, dotted with the wall vector, which we're just going to call AB, is 0, and this is going to be letting the wall vector be AB, like that. Okay, so we get that minus 3A plus 2B equals 0. And we only have one equation for this. However, we can just pick any values of A and B that work in this equation. So if we were to pick A as 2 and B as 3, okay, which would be the most obvious set, we get minus 3 times 2 plus 2 times 3, which obviously gives you 0. Therefore, the wall vector is 2, 3. Okay, and this is just, remember, this is not the magnitude of the wall. This is just a direction parallel to the wall. I'm going to say wall vector equals 2i plus 3j. Hence, AB parallel to 2i plus 3j. Okay, that's our first part done. Okay, so part B, we need to find the value of E, okay, and this once again lies with the only equations we ever use when doing angled wall problems. Minus EU dot I equals V dot I, and U dot W equals V dot W. Okay, these are the only two equations you'll ever have to use, okay, the only two vector equations for angled walls you'll ever have to use. Okay, so I is a vector parallel to the impulse, W is a vector parallel to the wall. So let's use these two equations to work out E, okay? Maybe we'll only need to use one if we're lucky. So minus E U dot I equals V dot I. So let's put this into place. So minus E U dot I. What's U? Well, U is 7, 2, okay? Dotted with I. Well, we know from our previous part of the question that I is minus 3, 2. However, if we were struggling with part A and we didn't know that, okay, we always know that the wall vector is perpendicular to the impulse vector, so we could just flip these two components, okay, so flip the 3 and the 2 and then make one of them negative, okay, and that'll give us our impulse. That's how you find a perpendicular vector to a 2D column vector. So minus EU dot I, so this is our U and this is our I, equals V dot I. Well, we know V, okay, is 1/6 from the diagram, and I is also minus 3, 2. Okay, those i's are always going to be the same. So this is our v dot I. Okay, so let's sort this out. So minus e times minus 21 plus 4 equals minus 3 plus 12. So that's going to be 9. Okay, so minus e times minus 21 plus 4. Well, that's 17e equals 9. So e is 9 over 17. And that's our answer to the coefficient of restitution here. So we didn't even need to use this u dot w equals v dot w. And the reason we didn't need to use it is because it has no e in. Okay, it has no use to us in this question because we want to work out e. And only this top one, okay, has e in. So this is actually our really, you'll see in most questions, this is the most useful one, this top one here. But often they need to be used in conjunction to sort out a pair of simultaneous equations. Okay, so that's often what you'll see as well, like in the first video I've made.